Let's welcome the first presentation, which is paper number 15. The authors are from National University of Singapore. I believe Miss Huan Ying is already here as the presenter. Okay. So can you start to share your videos and also audio? Okay, just a few seconds. I think they're working on some technical.
Okay, can you hear me?
Okay, Mr. Ying, yes, I can hear you perfectly. And yes, so basically you have 8 to 10 minutes, and I will give you a reminder at 8-minute mark. Okay, so the title of the presentation is Towards Beam-Based Robot Localization, a Real-World Case Study. So Mr. Ying, the floor is yours, please.
Thank you, Rombo. And hello, everyone. I'm calling from Hong Kong University, Hong Kong University of Science and Technology. And this work was done by me and my colleagues when I was working at US, Singapore. And today, in this study, I will present a robot localization, which is based on beam. And we present a real-world case study. The motivation is that in robotics community, people are doing SLAM or other mapping techniques to build maps, and these high precision maps are also with high cost. So in this way, we are considering how to convert BIM to a localization-oriented map, and in this BIM-based maps, we can use mapping-free localization, which means we can localize a robot without pre-mapping. We can just use a beam from the construction side to localize the robot. In previous studies, we noticed that there are many people are doing 2D CAD or 2D floor plans based localization, but these localization methods are based on 3D work. In this recent years, some researchers are doing beam-based robot navigation. However, these works were conducted in a simulation software. So in our study, we are doing 3D point cloud-based localization. The localization is conducted in 3D work, and we are delighted to perform LiDAR localization in the real world. So this is the framework of our study. We first convert the digital twin representation beam to the localization-oriented map, which is a point cloud-based map. Firstly, we separate the floors to submaps, and in each submap, we convert the.
And you can replace the microphone.
Pardon?
Juan, you can please replace the microphone. You have problems with your microphone.
Maybe move closer to your microphone, so your voice is a little bit dim.
Please.
Sorry for that. So in the first step, we convert the XC file to OBJ file, and but the OBJ file is not localization oriented. In robotics, people are doing localization on point clouds. So after that, we convert the OBJ to point cloud maps using cloud compare. Specifically, we are sampling points on the meshes and this sampling density can be decided by our human beings. So this is the whole pipeline of our beam-based map conversion, and after we get the maps, we can use sensors to localize the robot on the point cloud maps. In the localization pipeline, in this study, we use a popular method, which is ICP, Interactive Closest Point Method, to localize the robot on the map. At one timestamp or at one laser scan, we use the ICP to reduce the collected laser scan to reduce the error between the collected laser scan and the converted beam-based map. Specifically, we use a point-to-plane metric arrow, and on the right side, it is a ICP process demo on TD dataset. Well, in our post-tracking task, which is the localization task, we use the result from the previous estimation result as a guess for the next estimation task. So in this way, we can achieve a reliable post-tracking. To evaluate our method, we collect data in the real world. We collect 3 sequences in the university building, which is a very large building in US campus, and we use the Valentine sensor to collect the laser data, which has 16 beams at one scan. We compare our method to the state-of-the-art LiDAR SLAM, and the arrow is about 10 centimeters on translation estimation, and for rotation estimation, it is around 1 degree. We notice that most of the arrows are below 10 centimeters, so we can achieve centimeter level estimation, but some arrows are with significant values, such as in the second sequence, we notice that there is a gap between the ICP localization and the SLAM method. So we continually to do some research on this, and we find that there is a deviation between the as built and as designed. So the deviation really brings errors to our localization method. And here we present a case that at post A and post C, it is with a small lower arrows, because most of the data associations are correct. But at the post B, it is with a larger arrow, because the window latch, which is in the red box, it is there is a deviation between the as designed beam and the as built buildings. So most of the points are aligned to the wrong window latch. Fewer points are aligned to the columns. So in this case, the post B is with a large arrow. So the deviation really brings arrows to the robot localization in beam maps. So how can we reduce these errors in our future studies? We consider there are several promising directions. One is the semantic augmented localization. This is what we have done in the past 2 or 3 months. We generate semantic point clouds rather than just point cloud. We also color the point cloud maps, and we use the colored maps or the semantic maps to filter out some wrong laser scans. And in this way, the localization will be more robust and more reliable. Another promising direction we think is the global localization, because at the first step or in the first time step, we manually set the robot pose. But in robotics, the robot is required to localize itself from scratch. So global localization is more popular or in BIM. I think there are another direction is how to fuse the some other sensors such as MU wheel odometry to achieve a higher accuracy. Here is a video that we have done some work on semantic localization in BIM. So thank you all, and here is my email and address. If you have any questions, you can ask now or email me. Here I also want to thank the funding agencies. One is the Building Construction Authority at Singapore, and another is Hong Kong Center for Construction Robotics. So that's the end of my presentation.
All right, thank you very much. Thank you very much, Mr. Yin, for your very excellent, exciting presentation. And the time control is perfect. So Santiago, is there any questions from the auditorium? All right, so for the moment, if there's not any question from the auditorium, and also I didn't see a lot of questions from the chat, but maybe I would like to ask one, maybe just some quick thought or questions or comments. So basically, as I understood your project and your approach, you generate this, you use the BIM data and to convert it into this point cloud. So I was wondering if, what about what do you think about to handle this deviation in terms of the time axis, meaning that for example, if your building is not finished yet, and there are some parts, for example, is not completed, or some parts are partly under renovation or stuff like that. So how do you handle this deviation for the site and your BIM model? Is your BIM model keep evolving through time?
No, we just use the BIM in the built environment. You mentioned that in the construction status, when the building is not finished, I think the BIM-based map is not so reliable or can be trusted. I think another solution to localize the robot in BIM is that we can use a floor plan during construction, because BIM is changing in the construction side, but BIM is reliable in the built environment. That's my understanding.
Okay, thank you very much, Mr. Yin.